Now we'll see how to take care of life prediction of a component having notch. So how notch affects your fatigue life? We saw that naturally it is reducing, and how to go about using SN. So in practice, fatigue failure usually occurs at notches or stress concentration. Almost all machine component and structural members contain some form of geometrical or microstructural discontinuities. Discontinuities of stress concentrations often result in maximum local stress of the number S member. In ideally elastic member, the ratio of this stress is given by sigma max by S. So generally, if you recollect, capital S, small e is referred to external load, stresses and strain, but when it comes to local stress strain is sigma and epsilon. So this is maximal local stress. Again, though S is telling you about applied stress, it's not that a very generic word, but when you come to the practical problems statement and all, you have to be very careful about taking nominal stress, not the far field stress. So this is known as theoretical stress concentration factor from static point of view. This is calculation you are doing static content. We have not come to the fatigue yet. Also known as elastic stress concentration factor. This theoretical stress concentration factor is dependent on geometry and mode of loading that we saw in the previous slide. Now, when the same notch patient subject to the fatigue, there is one more thing comes, which is known as fatigue stress concentration factor. Subscript T corresponds to axial, and sometimes your structure may be subject to shear torsion, so it is shear TS. The formula remains same. Again, we are not so familiar with fatigue stress concentration. Are you familiar with? Have you used fatigue stress concentration factors? Yeah, because I will down the line will come to know. It's not known and popular and not used because we use conservative factors KT, because fatigue stress concentration factor is less than the stress concentration, theoretical stress concentration factor. So if you use stress concentration factor, with that if you are able to clear your objective, whether life or a thing, then no point going into detail, spending time, efforts to find out what is the fatigue stress factor. That is well said and is fair enough. But question comes, one has to be very careful about this. When again the situation where something you have to mitigate. So as usual, one way is you have to redesign where maybe there is a issue, time of things and all. You see whether is there any way you can clear it. So in that case, you can come to the practicality, fatigue stress concentration factor. You can use that, which is less than KT. That is one thing. Second thing is, whenever nowadays everybody asks me to correlate experimental data with theoretical data. So experimental data means actually the specimen or structure experiences with due to its own allay, whatever characteristic. Then theoretical, if you don't take this small factor like correction factor and fatigue stress factor, you will never able to match with that. There will be always difference. So for that two purposes you need to know. But in principle, as rightly pointed out, nobody uses thing. Because I also will down the line say it's not straightforward. Like KT, what you refer to the Peterson, get the value for a given geometry. Or DFM, if you don't have anything, you can do the DFM, find out. But here you will find it's not a direct, not handbook referred. You have to, of course, you have to refer for some other data. Indirectly, you have to calculate the fatigue stress, but that will be useful when you want to do correlation or you have to have a mitigation at a critical stage. Some materials when fatigues are not fully sensitive to the presence of notches, and hence a reduced value of KT can be used. In the stress life approach, the effect of notch is accounted by the fatigue notch factor, that are fatigue strength reduction factor. I think somebody was telling about rating and all. It will reduce and all that, most appropriate to your fatigue strength reduction factor, not the KT. Because once you talk about fatigue means always you have to, just because we are not familiar with the familiarization with KF, we generally talk about as KT. So it is defined by fatigue strength notch strength of smooth specimen at 10 to the power 6 and fatigue strength of notch specimen at 10 to the power 6 notched and smooth. So what do you expect? Kf, is it 0, equal to 1, or greater than 1, or less than 1? Of course cannot be 0, it has to be value 1, but is it equal, less than, or greater? Solution clue is there in front of you, the figure. Correct, because you are comparing fatigue strength at 10 to the power 6, this is what? Greater than this value, right? Obviously it will come greater than 1. So your endurance limit, so 10 to the power 6 you are telling the endurance limit. Again, please remember, it's a ferrous 10 to the power 6, but for non-ferrous you have to take comparison of 5 into 10 to the power 8. In that case, stress level will be less. But as usual, as a conservative, you can take 10 to the power 6. That's not a wrong, but practical sense, there is no endurance definition for non-ferrous material, and benchmark is 5 into 10 to the power 8. So you should compare not as for Kf, not at 10 to the power 6 for aluminum, it is 5 into 10 to the power 8. So your Kf lies between 1 and Kt. So if Kf is equal to 1, that means it's not sensitive to notch. And if Kf is equal to Kt, is a full notch effect, where Kt is the elastic or theoretical stress concentration factor. This is what you can see here. You have a round bar axially fatigue tested with 6.35 dia. That's a smooth one, you get the SN curve like this. This is the experimental data. But to test it, if a Kt is equal to, where is that Kt? Somewhere it must be there. 2.43. And 6.35 is the thickness to maintain same dia, but you are having a double notch, which results in Kt of 2.43. Same material, same fatigue level, you see how they are getting. It is very widely difference at the higher, at 10 to the power, 10 to the power 4 onwards. Here there is nothing much. 10 to the power 3 anyway, beyond less than 10 to the power 3 is low cycle fatigue, you don't worry. 10 to the power 3 is, but it starts remarkably differ from 10 to the power 4 onwards. So you get this thing. Effect of notch is accounted for in the same manner as low type. So again, endurance limit, if you have SN curve available for notch, that is again material. So if you want to apply to the component or structure, again you have to do those correction factors. That values remain same everything, but you have to apply again. It has to scale down, knock down, like C load, surface Kj and divided by K. And it is depend on the material as well as local geometry and is generally less than Kt. Okay, so it's also depends on the material with the same type of geometry, but whether it's made of ferrous or non-ferrous, your Kf is different, and local geometry is